All right, so it's my pleasure, it's our pleasure to have Sascha Meier here. Sascha is a professor in ECS at Berkeley, and she also directs the Energy Grid Research Program at the California Institute for Energy and Environment. She is also a faculty scientist at Lawrence Berkeley Labs. So Sascha has worked on a lot of very important projects, and one of her sort of seminal contributions is the development of MicroPMUs. And in this talk, I think she'll talk to us about how to do Phasor-Based Control of DERs. Please take it away.
Thank you so much. It's great to be here. Thanks for having me. I'm going to tell you a little bit about a research project that we completed very recently at UC Berkeley, Phasor-Based Control. I understand that the audience is pretty mixed in terms of, some of you are working deeply engineering much. So I want to encourage you, if you have a question, I might not be able to click on the chat window, so don't worry about being impolite, just interrupt with questions. And some slightly bad news, my computer just said that my internet was unstable. I sure hope that's not the case and it will recover. It's usually really good, but apologies in advance. If something goes badly, I will send a PDF of my talk to Bausen to share. So in the big picture, what are we trying to do? We're trying to accelerate the necessary transition. I will not belabor why it's necessary to go to, but part of what has to happen is we have to put solar and wind wherever we can. We also want our grid to be reliable and to be resilient with respect to failures that can come from climate-related events, as we know in California only too well with wildfires, storms, but also cyber attacks and who knows what. So having resilient distributed generation is a really important policy priority. And we want to be able to make distribution grids able to accommodate as much solar generation, but also as much electric vehicle charging as possible. And that's a constraint that I think is going to become more and more painfully apparent in the coming years as we move to shift our transportation sector over to electricity. That's a lot of load growth. So it's accommodating both the generation and the new loads. This research project I'll talk about specifically has developed and was testing out sort of a proof of concept of a new control strategy. The idea is that we want all these distributed resources to play nicely together and to be good citizens on the electric grid, rather than being erratic in their behavior and causing unpredictable problems. We want them to respond to the conditions on the grid as they're measured in real time. And the challenge with that is it takes information to know what's the right thing for a controllable resource to do. It's no longer rocket science today, or at least it shouldn't be, to program solid state devices to behave in any way that we would like them to. The trick is mostly knowing what to tell them to do. But we also need fast response for rejecting disturbances and basically keeping things mellow on the grid. And I think that that will be very difficult to achieve with economic incentives like real-time pricing, because the time increments that you need are pretty fast, pretty short. And so this project is about a way to control resources based on direct measurements. This project that we just finished was funded by the Department of Energy, had partners, the Lawrence Berkeley Lab, University of Michigan that worked on a control algorithm, OpalRT that does grid simulations at very high speeds with lots of data, GridBright that works on publicly available distribution circuit models, and everything that we produced for this project has been Pink Things that has database predictive grid to deal with streaming measurement utility. People worked on this project. It was a 3-year project, so some students and postdocs came and went, and it was a real privilege to work with everybody on this team. So let me outline the big picture of what we're trying to accomplish, sort of like it's presented in this diagram. The idea is that we have a desired operating state of the electric grid, a desired steady state that can be mathematically voltages. Phasors, which include voltage magnitude and angle, or the precise timing of the voltage waveform, describes everything that there is to know about power flows in the grid. That is, real and reactive power flows, the exact timing is all encapsulated in this information. And in this phasor-based control paradigm, a supervisory controller computes what the desired state of the grid is. That is just an optimal power flow calculation. It expresses this in terms of voltage phasors that can be assigned to different nodes in the system. So for those of you not familiar with the notation, V naught would be a reference voltage magnitude, and then this angle delta would be a reference angle, or the time of the zero crossing of the voltage waveform. And if we know these voltage magnitudes and angles for these different locations, then we've completely described the power flow. In this control paradigm, there is a supervisory controller that computes the targets, and then there are local controllers which will drive the local resources or actuators to meet those targets. Now, as I said, the idea is to do this faster and in a more direct way than I believe we can do this with price signals. Pricing can accomplish a lot of things in electric grids. You can have real-time pricing, locational pricing, because in fact, the value of what a resource does at any given instant depends exactly where it's located. Here we're going down to a really granular resolution, where a resource down the street should be doing something different than the resource up the street. Now, if we try to do this with prices, what we would have to do is we would have to translate the state of the grid into prices that are designed to evoke the proper behaviors. So we're kind of going from physics to economics and then back to physics. And we need to understand how participants actually respond to prices, and then how will real devices be controlled. That means there's going to be some corrections that have to happen. You need to have a model of the circuits that you're working with in order to calculate exactly what the behaviors are that you want. There's complications about phase imbalance in a three-phase system. You may want someone on phase A to do something different than someone on phase B or C. So it gets very complex when you go down to this fine granularity. In the phasor-based control concept, we're dealing just with physical measurements. And in a sense, that's analogous to the way that we control large generators on a voltage regulator and on frequency droop control, where the machine is responding to quantities that it can measure rather than what somebody else calculated. And you may update set points later. You might take minutes, seconds or minutes to give a generator a different set of set point instructions, but from a moment-to-moment basis, the machine knows what it needs to do just by measuring. The idea here is, instead of measuring frequency, which is kind of a global system-wide metric for power balance, we're measuring these voltage phase angles, which are a local measurement that corresponds to power flow locally on the grid. So the device control decisions are made directly in response to these measured quantities, which means you don't have to wait for people to compute a lot of things. You're making these fast decisions entirely in the realm of physics. And the idea is that the economics of who needs to get paid how much money for doing this can be taken offline and can be done more slowly, so that everything the devices do, in effect, could be thought of as an ancillary service of being available to perform this response. Now, in order to do this, the MicroPMUs are an essential enabling technology, because you have to measure the actual state of the grid with quite a lot of precision. So this is the technology that we developed in an ARPA-E project that seems like ages ago now, to make it possible to measure these quantities that I described, the voltage magnitude, but also the phase angle, which is the exact timing in small fractions of a cycle, where a cycle would be a 60th of a second. So we're really talking about milliseconds here. And in order to make those measurements, you have to have the same reference clock. So phasor measurement units became an option when there was inexpensive access to GPS timing. And these MicroPMUs, which are designed especially for distribution systems, where you have ever so slight timing differences on the order of degrees or fractions of degrees within the 360-degree cycle, that takes a very precise timestamp and a high-quality GPS receiver. So that was really the technological innovation here. And just to show you some illustrative data of what these measurements look like and how the voltage phase angle relates to power flows, here's some example from a field site where we tested these MicroPMUs, and we're comparing the voltage phase angle between the substation on a distribution circuit and where a large photovoltaic array is connected. And so in blue, you see the amps, the current, that's roughly the power flow the power that's being exported from what is obviously sunshine. And then in red, you're seeing the voltage phase angle difference, that is the phase shift between MicroPMUs 1 and 2. And you see here, this goes from -0.5 degree to +1 degree. This is mixed in with load. So really, the phasor difference is showing kind of a net power flow on this line, and we don't have measurements in this picture from the load, but the solar generation is kind of dominating this picture. And so you can see very well how the phase angle difference correlates with the power flow, and also the fact that you need to make some really precise measurements to get any information out of this. For those of you who are into power flow equations, you're probably familiar with this approximation that is often used in the transmission context, where transmission lines have very little resistance so that they don't overheat and lose energy, but they have quite a bit of inductive reactance, quantity X. And in the approximation where the inductive reactance outweighs the resistance, generally we can say that the power that's transferred from node 1 to node 2 is roughly the product of the voltage magnitudes divided by the inductive reactance times the sine of this delta 1, 2, which is the angle difference, the voltage timing phase angle difference between two locations. So that's not always a good approximation for distribution lines, because by virtue of their smaller physical scale, the inductive reactance is not so dominant over the resistance. The resistance can play a big part. So a better set of approximations are these Lindis-Flow equations, which relate voltage magnitudes to both resistance and inductive reactance, both R and X, and to real power flow P and reactive power flow Q, where the reactive power is the power that oscillates through the system in order to satisfy the time lags of inductive and capacitive devices that are everywhere. So what happens when you have appreciable resistance, these quantities get intermingled, and the phase angle difference, which we could have a sign here, we're making a small angle approximation, is no longer just related to real power flow, but also to reactive power flow and resistance. So it gets more complicated, and this is kind of a foreshadowing that the ratio of R and X is an important determinant of how a control system is going to work, because again, these variables are coupled together. But it's common at the transmission level for operators to think about phase angle differences as being indicative of real power flows. This is one of the great resources provided by the University of Tennessee at Knoxville with their FNET monitoring system that shows you basically in real time with very short delay these voltage phase angle differences, which across the entire Eastern grid go over many, many degrees, because we're talking about many megawatts and long distances. So large impedances, or especially inductive reactances on the transmission lines. But you can see that power is generally flowing from areas of positive phase angle to areas of negative phase angle. So this kind of intuition is already common at the transmission level, but we've never used it for direct control of resources because the phasor measurements were not as easily available, and because the system is still set up to really operate on droop control, which has the benefit of not requiring any communication, right? Droop control just being generators responding to changes in frequency by adjusting their output. Now, interestingly, for voltage control, we're already doing automatic voltage regulation, where generators are injecting as much reactive power as it takes to maintain a certain voltage magnitude at their bus or interconnection point. In transmission systems, because of that dominance of X over R, it's sufficient to just use reactive power to manage voltage magnitude. In distribution systems, all these variables get mixed together. So the concept here is, what if we control all of it together? So I have a couple of graphs to show, to sort of try and motivate that. And I realized that a terrible formatting thing happened. My angles moved around because I opened the PowerPoint in a different version and the size of the font changed. I hate it when that happens, but you get the idea. So we have two locations where the voltage phasor is being measured, and that difference corresponds to the power flow along this line. Now we have a distributed resource here, and it could be a solar array with an inverter, it could be a battery with an inverter, it could be a smart EV charger or an aggregation of loads, anything that could be controlled to have a modulated power injection or power withdrawal. Now, what should this resource be doing? Generally speaking, in a price-based system, we're thinking, well, it should act to alleviate power shortages when there are transmission constraints, or where there's, when we're tight on generation resources, it should be injecting more power. Otherwise, it should hold back. If the voltage is too high on this end of the distribution feeder, it should inject less. But to be really responsive on a short time scale to everything that's happening, what we'd really like is for this resource to actually compensate for what its neighbors are doing. So when there's uncontrolled solar resources, for example, clouds pass over the solar array, or you have big loads coming on, all these disturbances could be counteracted in real time by this good citizen resource that's watching what its neighbors are doing and then directly compensating for it. For example, to hold the power flow at the top of the distribution feeder at some constant value, or keeping it below some threshold, for example. But now there's a privacy issue. You don't want to, you can't actually observe directly what your neighbors are doing. You could measure the current at the feeder head and say, well, why don't we just hold that current constant? But by measuring the local phasor, we're getting more granular information actually about where that net power is coming from, and whether there's a lot of demand or overgeneration at the very end of the feeder that we might counteract, or whether it's closer to the top of the feeder where it doesn't make any difference. So we're getting more locational information in that phasor. We're also able to observe changes in topology. If there's switching operations that might affect what is a safe operating state, you would be able to observe that in the phasor, but not by just measuring the net current. We're also able to address both real and reactive power. And again, we're not compromising privacy by having a measurement that reflects the behavior of everyone without revealing too much, because you can measure these phasors near a node and get the same answer without having to put a current transformer or current sensor on the circuit branch that belongs to an individual customer. So you can kind of access the information more discreetly. Here's another intuition about why you would want to do phasor-based control at the transmission level, where you have, in this hypothetical example, two parallel lines that connect two nodes. And again, I apologize for the formatting. Suppose that you have a transmission line outage. So what you would really like to do is to manage the power that's generated at node 2 here, to essentially be responsive to any constraints that occur on this transmission line. Now, in order to convey that information without phasor measurement, you would have to go through some other computation that recognizes, oh, a transmission line went out, and now that this line on top has to carry the entire power flow from 1 to 2, maybe that's at risk of being overloaded. We're no longer in a secure state. So we need to, let's say, reduce load or increase generation at bus 2. Someone would have to calculate that and then convey that, relay that message with some price signal or some request from resource 2, but that requires a little processing and computation. What we're proposing here is that by the direct measurement of the phasor, without having to have any information about the nature of the contingency or the nature of what just happened, what just changed, this resource will be able to observe a sudden change in the phasor difference. As this transmission line goes out, if those were the same, the impedance now doubles. And so the phasor difference is going to roughly double for the same power flow. Now, in reality, power flows are going to realign themselves, but this resource will be able to observe that something happened instantaneously and will then be able to act to restore the phasor profile that was there before, which is guaranteed to be a safe operating configuration, because we know that that phasor difference will not overload the remaining transmission line. So by driving this resource back to restore the phasor difference that was there before, regardless of the nature of the contingency, it is acting to stabilize the system. And you can show that in a rigorous way, that it will be acting to drive the system away from a possible voltage instability or angle instability, and also away from a possible thermal overload. So that buys time for someone who's actually doing an optimal power flow calculation to say, all right, the topology has changed. We now have reallocated power flows. We're no longer economically optimal because maybe this resource just kicked in a bunch of power generation that was quite costly. So a supervisory controller that has information about costs can then do a calculation to reallocate and choose new set points, issue new targets based on what is the new network condition. But you can enjoy the luxury of taking a minute to do that, because you're not going to lose that much money in the first minute or so. And you have improved the stability and reliability of the network and bought time for the optimization. So you're doing the physics first, and then on a slower time step, re-optimize. So that's kind of the general idea. And our project was about seeing, could this be done in practice? Or at least in simulation, but with some hardware in the loop. So some points about the supervisory controller here: it really doesn't care what criteria you're using for your optimization. It doesn't care what the optimization is about. It just needs to be able to run the power flow, and we'll talk about what some of the challenges are, but it can take its time. It will use some compromise between a full nonlinear power flow and something that's linearized in order to get an answer more quickly for large systems. And the test cases that we looked at were some very distribution-specific test cases, because even though I envision this system as being scalable across many layers of transmission and distribution, we really needed to show the proof of concept that it can work from the bottom up at the distribution level. So just in the illustration here, in the sample illustration here, we're trying to enforce a particular power flow at the feeder head across the transformer. So that means holding constant the voltage phasor difference between the reference and this performance node, the target. And so we tried a lot of different configurations of where are actuators that we're going to control in a feedback control, trying to keep this target, trying to keep the phasor matching this target relative to the reference. So this would be an example of the net power flow control. You can use this to balance the three phases, A, B, and C. You can use it, as I said, to reject disturbances, managing voltage volatility. When the crazy stuff your neighbors are doing is driving the voltage up and down erratically, you can have your resource watching the voltage and counteract that in a very deliberate way. You can also choose, for example, a performance node out at the end of the feeder where it might be, there might be a tie switch to connect it to a neighboring circuit. And you could watch the phasor on the neighboring circuit and drive the phasor at your end to the same value, so then it becomes safe to close a switch. and it can help you reconfigure the system on the fly. We also looked at really, where's the business case here? None of these applications right now are worth millions of dollars to justify the infrastructure that you'd have to roll out with all the MicroPMUs. But where the money is in transmission outages. If you're trying to keep the system secure, and that constrains what you're able to do. So we did some value scenarios where we said, well, suppose the whole distribution feeder has phasor-based control and is able to just actuate all of these resources to maintain a certain power flow at the substation or to adjust as needed from the transmission level. That's where probably the near-term benefit would be. So we then experimented with a couple of different variants of local controllers. We experimented with inverters, batteries, and controllable loads. They could be single or three-phase. Some of them are limited to just actuating real power, a heater, that's all it's going to do, more or less real power consumption. But with inverters, you would expect 4-quadrant control, so they could do whatever you ask them. And we showed generally that we can track a phasor target on distribution circuits and reject disturbances with a pretty short control time step. That ended up being limited by the interface to the inverter control loops, which the manufacturers like to have in their proprietary little boxes. And it turns out to be a royal pain to get in and explicitly tell inverters how much P and Q to give out. The inverter manufacturers like to just have you give them general instructions and then they figure out the details under the hood. So that is actually one of the biggest roadblocks, I think, to the field implementation here. But we tried multiple local phasor-based control algorithms that all worked, and they have different pros and cons that I'll talk about. A simple proportional integral controller works great. A linear quadratic regulator that's a multiple input, multiple output controller works even better, but it needs a network model to do this. Whereas the PI controller can just figure out from empirically what it needs to do without having a circuit model. And then there's a retrospective cost adaptive controller that the University of Michigan developed that basically looks back at its control decisions and then improves them going forward, which works really well. These are just some graphs, and we have so many of them, it's sort of hard to decide which ones to show you, but just some examples of how the voltage magnitude at the performance node dips down or goes in different directions on the 3 phases here. Red, green, and blue are ABC phases. And then the controller restores it to whatever the target was, the magnitude target, 1.02 per unit in this example. And then comes another big step change disturbance that we programmed in, a huge load change, and the controller actuates the distributed resources to bring the voltage magnitude back. And it does the same thing for the angle here. The disturbances are less obvious, but it drives the angle back to the set point. And these graphs just show the real and reactive power that was recruited at the actuator nodes. And those are some pretty big numbers, right? 1 or 2 per unit. And therein kind of lies the rub with the conditioning of the problem, because it takes a lot of kilowatts to affect an angle change of 1/10 of a degree or 1/2 a degree. But it works. Here are some pictures from the Flex Lab, where we have these 3 Solar City inverters. And don't get me started complaining about how whispering to them through their API was challenging. We have some transformer bank here, There's a MicroPMU GPS receiver. That's how it knows the precise timestamp. And then there's the Opal RT simulator down here. These are load racks. So these are groups of fans and controllable loads that are kind of lumped together that we could turn on and off. And there's Maxime Baudet pretending to work on a MicroPMU, because you may ask yourself, what is a photographer doing in this room? We were only allowed during COVID to have one person on site. So this was a photo session after the fact. But it shows you nicely how we have the MicroPMU set up here. You can see the power walls in the back. And I was actually really relieved that we figured out a way for everybody else on the project to work remotely while Maxime was the only person on site. This was in June, July of last year. And we were able to actually implement this. Another just word about the communications infrastructure. We're able to leverage this wave message bus developed by our colleagues, in particular Michael Anderson and Gabe Fierro of the ECE department at UC Berkeley. That is a publish-subscribe message bus, which allows for a secure way to multiple actors to communicate sensitive data and decide who gets to see these data without having to trust a central authority. And it was really important to us to develop this infrastructure that would be possible to roll out in the field with different actors, different parties who don't want necessarily their neighbors to see their data, but everybody is able to subscribe to the data that they need in order to make the right control decisions. In this example, we have these local message buses that connect to the Wave pub/sub bus. You could use other SCADA data, forecast prices for your supervisory control optimization. We didn't go there because we figured that's a solvable problem. We know how to do that. We focused on the local implementation. You would have the MicroPMUs measuring and putting those sensor data on the bus. The supervisory controller has access to whatever cost or availability data the resources want to provide it. It makes decisions about phasor targets. Those phasor targets get published. And then the resource, the local resource, can subscribe to those published phasor targets and drive its own resources. It will have a local PMU measuring its local phasor and comparing it to the reference that was assigned, that it gets through the message bus. So we do have a vulnerability here. We depend on communications because driving your local phasor isn't enough without a reference value. But we've shown that you can fail safe if communications goes down for whatever reason. And so this is extensible to large numbers of resources. And then you can also put analytics and fancy features on top of this. And we exported the data to cloud services so that we could then archive all the high-res phasor data streams, and you can do lots of more analytics on them. Let me just quickly show you some sample results. And there's, again, lots and lots of examples. This is just an example on 3 phases where we have voltage magnitude on the left, voltage angle on the right, and we just programmed in disturbances, misbehaviors on the part of other resources on the distribution circuit. Opal RT simulated one at a time, but we had 30 different circuit models that we used in simulations. And DOE really wanted to see big circuits. So we took a 341 node feeder that was sort of a realistic PG&E feeder. to work with that as well. But so you see these disturbances, and then each time the disturbance happens, the phasor-based control drives the voltage and phase angle back to the target, which is this yellow line. So it's restoring power flow as it was before. This was done with the PI controller. Now, the MIMO controller, the linear quadratic regulator, is much faster. It has information about the network model, so it can discern between the results of its own actions versus changes in the network. And so it can respond much more intelligently. And these disturbances are almost instantly rejected within a single controller time step. And this is inverters being actuated. So here's this large PG&E feeder that we put into the Opal RT. And it's very jiggly because it has constantly varying, lots of big varying loads. But in the process, the inverters are tracking their targets still within reasonable accuracy. One big test was to see what would happen if the supervisory controller gives a target that the local controller just can't reach. And you'd have to expect that that would happen if it had, insufficient information about the capacity or availability of the local controller. So in this example, there was a change of the assigned phasor target from yellow to green. And this was a battery that was asked to consume more power. The battery should be charging to bring the voltage down. And it couldn't bring it down that far. So we implemented this feedback, which we called the I can't do it, where the local resource communicates to the supervisory controller saying, hey, your target, I can't do it. Give me something more reasonable. And the supervisory controller then reissues this red target. And the actuator says, okay, we can get there. So that was an important demonstration of the robustness of the system. So in sum, a fundamental challenge in this problem is that it's just not well conditioned. You're measuring a tiny quantity with tiny differences, and it corresponds to a small error in the phasor measurement corresponds to a large error in the number of kilowatts or kilovars that you want to dispatch. But we showed that it is doable under what we think are very realistic assumptions. It's maybe not practical to do for 10 kilowatt loads, but 100 kilowatts is a great sweet spot for this. There is an obvious trade-off in how carefully or accurately the supervisory controller optimizes versus how quickly it can do that. And I'm sure some of you are experts in this area of power flow linearization and figuring out how to sort of have the most practical compromise that will reliably get you a result that's good enough soon enough. So we've worked with an iterative calculation and a loss approximation method. Thirdly, I mentioned that we can't enjoy the luxury of assuming that we have a perfect network model. In distribution systems, that's just not the case. So we showed that both the PI and the RCAC controller algorithms are able to observe the responses of the network to their actions, and the controllers could be tuned, and we could find gains in almost all circumstances that would then drive the system in the way that we needed to, without having a priori information about the model. That can be confounded if you have a lot of coupling between P and Q, which you get when there's a lot of resistance in the circuit. And we developed another analytic tool for sort of identifying when those constraints become important. The alternative approach is to use the network model in the controller. And that works great when you have it. Scaling, which was DOE's big question, is not that big a problem from our standpoint. We could show that controlling larger numbers of actuators and nodes works nicely. There's some situations where the controllers would fight each other, and we sort of outlined what those cases are, or how you would discover on a circuit when those adverse interactions might happen. And we also began to look at how you layer this into the transmission network. Really, the biggest challenge that I see to a near-term rollout in the field is those inverter APIs. Having the inverters listen to what P and Q they should produce, having the inverter manufacturer let you into that. So, you know, one possible path as a tech to market strategy is to have the inverter manufacturers just incorporate the phasor-based control into their product. Then they don't have to tell anyone. In conclusion, it basically works, which I wasn't sure whether to expect that it was going to work. And my belief is that negative results are still good science. So when I recruited students and postdocs to work on this, I told them, hey, you know, this might not work. If it works, it'll be really cool. And it does work. So we could track the targets to within 5/1000ths of a unit, which was our performance target for being useful in practice. We can reject step disturbances of 100% of the capacity of neighboring loads. And so we really can shape the power flow on a distribution circuit and by extension on transmission systems if enough resources participate in this. And we've shown that there is a path to secure communications. So what I want to do next is put this in the field, but I should pause here for Q&A and discussion. And, you know, hopefully at some not too distant future time, come back and talk about where we actually did this in practice. Here's a list of papers that have come out of this so far, and it's in the fine print, but you know, I'm happy to send you any of these and happy to take questions.
Great, thanks, Sascha, for this great talk. For questions, let's do it. So for any of the student who's here, maybe you can ask your questions since you guys have a time limit. So any of the undergrad, graduate students who's taking this course, do you have any questions for Sascha?
I had a question for this talk, great talk. So when you say that the inverter resources do get a limit, which they cannot, like the batteries cannot go down that voltage. So why can't they do just what they are maximum capable of? How does that work in comparison to them sending back to the global controller that, hey, I cannot do this and give me some new set points? What about them doing their best and the global controller taking that and reorienting the angle and voltages for that?
Great question. So actually they will do that. They will do their best, but they will saturate the controller. So the idea is that the local controller would like to get some relief from having a non-attainable target, so that it can basically have a sense of how well it's doing rather than being just saturated and spinning its wheels. But you know, the recomputation that you propose is exactly what we're doing, where the supervisory controller looks at, well, what is the best that this local controller can do, assuming it's pegged at its maximum output, and on that basis recalculates it. So it's basically like sending a message back to say, hey, what you're doing is fine, just keep it there.
I see. Okay, thank you.
Okay, any other questions from students?
Hi, Professor Meier. Yeah, thanks for your talk. And I'm curious about how do you implement the control with respect to the phase angle? Yeah, because when we say the power flow, we will say that usually the differences of the phase angle in different nodes, yeah, will matter more. So if we just know the local information of the phase angle, so yeah, how we implement such control in the wide range.
Excellent point to highlight. Yes, so we need to have access to the reference phasor and compute the difference. So through the same communication channel that we get the target, and we get the target that might be updated on a slow time step, we would continually receive the measurement values from the reference phasor, and we continually take the difference. Luckily, that subtraction is a very fast bit of arithmetic to carry out. But the vulnerability is, of course, that if we lose communication, we lose that reference angle. And now if the system were at a completely fixed frequency, then it wouldn't matter. But of course, the frequency of the system changes a bit. So the reference is going to float, and then we will no longer be able to control the angle. So in the event of a communication loss, we have to satisfy ourselves with managing only the local voltage magnitude. It's conceivable to combine this control approach with a frequency droop control, and to say, well, we may also observe frequency. In fact, we might do some combination of local flow management with phasor differences, as well as observing the frequency or changing between one and the other. But you're exactly right that in order to manage the power flow, we need that one non-local piece of information. Luckily, it's not from very far away, so it doesn't have to bounce around through many different places where it's processed. It can just be published to the message bus and come right back down. There's very short latency.
Yes, thanks a lot. Yeah, and then one more small question. So yeah, to compute the reference angle, yeah, do you assume that we have some kind of operator who has the core information of all the system viruses?
So I think what you're asking is, how do we know what's a good choice of node for the reference node?
Yeah. Yes.
Which in the radial distribution system is pretty obvious. You know, in the radial distribution system, we would just say, okay, compare everything to the feeder head. But in a mesh transmission network, it's not at all obvious. And I didn't include slides in this specifically, but for a mesh transmission network, you would have to have some sort of strategic knowledge of the grid and the typical power flows and constraints that you're interested in managing in order to make good choices for what would be a good reference node. Because in effect, you'll only be able to drive power flow on, you know, one meaningful path with a set of resources. So that's a more complicated problem. And there are probably many possible solutions. I think you're right that you would expect empirical, you know, experience, operational experience to inform where you would place those nodes.
Yeah, I agree. Thank you very much.
Okay, any other questions from students? Okay, so if not, all the students, you can go. So let's open up the question for the rest of the audience. Anything from the rest of the folks who's here? Okay, so if not, there are a couple questions in the chat, so I'm going to read them out in the chat. So Sabash asks, what communication protocol does the message bus use?
So several. There's actually a wave protocol. There's God, let me see if I have the. No, I don't have those slides. There's numerous different protocols that that you can implement. I think, let's see. This actually shows that we have Modbus in talking directly to the devices, which is one common standard. For the PMUs, the C37 protocol, C37.118 is the regular standard. But I think the important thing to point out is that the message bus is really agnostic to the format, right? It can accommodate multiple different formats. Somebody can publish something in one format, and as long as whoever subscribes to it can read that, that works. So we're not limited per se. This is what we implemented here, but it's, it could be other things.
Okay. Other questions from folks? Okay, so if not, thanks again for the great talk. I think, Emily, we can end the recording and we'll transition to the next.